Homework that's over the weekend. It's just one or two topics I want to talk about. The introduction to rotational motion. Let me just go back to the screen. I believe if somebody says something, I can hear you, but I'm not sure. I'm hoping that you can hear me. I don't have my mic, but I'm speaking loud enough. I'm in, as you see, I'm in a different space. I had to come to campus today to do a laboratory inspection for our research. So I'm going to give the lecture at my chalkboard in my office, which is not quite as dark or pretty as the one I have on my home, but it should do the job for today. So today, the only thing I want to talk about is the idea. Okay, so we're going to talk about rotational motion. This is the last, I will call it a technical module for the whole course. It's the, everything after this is sort of gravy, but we have to talk about what we mean by rotation. Since I'm here, I've grabbed a prop. So this is a old bicycle wheel, which has been attached to an axle. And if I take the wheel and I spin it like this, I'll spin it this way. Okay, so that's, from your point of view, that's moving in the counterclockwise direction. So I want to talk about the wheel and its motion. And of course, the wheel has can be described in terms of different kinds of motion in different ways. So for example, the wheel could be just moved from left to right, or up and down, or into the towards you and away from you. So this corresponds to its position in three-dimensional space. And as you'll see, I've got a nice little video clip over the weekend where I talk about the kinematics of rotational motion. This moving side to side, this corresponds to what we call translational motion. But if the body is either independently or just otherwise not moving, but is spinning like this on its axis, we call this rotational motion. And it's distinctive in the sense that the parameter of motion is not displacement in space, but displacement in angle. So you can see there's kind of a white, well, it's not really white, it's kind of a beige marking right about here, I guess it is. If I call the heading corresponding to off in the x direction, so we're going to call that the x direction over there. If I call the angle when this beige thing is basically in that direction, I call that zero angle. Then this is increasing, so maybe that's about 45 degrees, and that's about, that's about 90 degrees. That's 180, and so on and so forth, all the way to 360, and then it starts all over again. So rotational motion is limited in the sense that there's an angle, but of course the angle can keep increasing and it just rolls over. And so that's the position, is the angle. So I could call that angle relative, the angle of this object relative to the horizontal theta. So let me just mark that on the top for it so we can see it. So I've got a circle like this, and if I, that's my wheel or my disc or anything that would rotate about an axis. And I'll call that the, basically a reference position corresponding to zero. And if I have some mark on the wheel as it's moving, I can measure the position of the wheel in terms of some angle theta. And then, of course, once I've got that wheel here moving, I want to talk about the motion. So again, there's the video clip goes into details about the kinematics, but the idea is pretty simple, that the rate of rotation depends on the change in the angle. So I just take a derivative to get that. So if I want, so this is theta, is my position, then d theta dt, which I will call omega, the same omega we had for circular motion because it's a very similar idea. This is my velocity. So I will call that my rotational position. This is my rotational velocity. And then, of course, if I ask, well, if the wheel speeds up, if it accelerates, then the time derivative d omega dt, which I will label alpha, that's my my acceleration. So the kinematics are actually pretty straightforward, but just by analogy with physical with translational motion. The only key thing to remember is that this angle theta is not a distance; it's an angle. The position is given an angle, so the units are different. If this was x, then the units would be in length or meters for SI. But for angle, the units are either degrees or radians, whatever. Radians are the sort of standard. And in that case, that's basically corresponds to a unitless measure, right? So omega is in radians per second, and alpha is in radians per second. So it's a different kind of unit. So everything's done by analogy for this kind of motion. So, and I've sort of set up an analogy table in the review sheet, but I want to focus in particular on this issue of acceleration. If the wheel is spinning and it's speeding up, so that's alpha, how do I describe the dynamics of that motion? What actually causes that motion? So I want to make what I'll call an intuitive argument as opposed to a mathematical argument. So the question is, what do I need to do to get this wheel to start spinning? Oh, hold on, let me just make sure everything's good working here. Yeah, it looks okay. Yeah, it looks okay. All right. Good, I'm just checking because I don't have the same feedback. Let me put in my ear this time. All right, fine. All right, so I have this wheel, and let's say I want to get this wheel spinning, and I want to get it spinning faster and faster. What do I do? Well, obviously, part of the job is applying a force. So just like regular Newtonian mechanics, forces cause things to happen. But not just any force will cause the wheel to spin. So for example, if I apply a force like this, if I hit the wheel straight perpendicular, the wheel doesn't spin. In contrast, if I hit the wheel at a glancing blow, like that, the wheel gets going. There's also the question of where I hit the wheel, right? So if I push on the wheel I give a push on the wheel at a very small radius, say really close to the axle here, I give a push, well, that wheel will start to turn. But if I give the same push over here, it turns much easier. So it's not just a force that causes the wheel to turn, but something else. I don't need, it's not merely applying a force. I have to apply a force in such a way that I put a twist on the wheel. There's this twisting idea. So if you ask the fundamental question, in terms of English language, what is the concept that causes the wheel to move? What is the fundamental dynamical cause? It's whatever we call a twist. And the physics language for this twist is torque, T-O-R-Q-U-E. So I want to basically come up with a what I will call a operational definition of torque. And the operational definition is, well, clearly, all right, so I'm going to use the Greek letter tau for torque. And this is a definition. So again, 3 lines. I'm basically coming up with a way of describing what the torque is. And what I'm going to argue is that the torque is proportional to the force. So obviously, if I apply a force, so this is a torque that would result from a particular force. So I'll call that tau sub F. And it's obviously, I'm going to argue that it's proportional to torque. And it's also proportional to, depends on where you apply the force. So I just argued that you get a much better twist on the outside of the wheel than you get on the inside of the wheel. So I'm going to, without proof, argue that the torque depends on this value R, which is the location where the force is actually applied, R. So it's not the radius of the wheel, it's where you put the force. And then there's one more thing, and that's the angle, because of course we argued that if I apply a force radially, it doesn't cause anything to move. I have to apply the force. I get the best twist when I apply the force tangentially relative to the wheel, which is to say perpendicular to the radius. So I'm going to put that perpendicularity in as a sine function of an angle, which I'll call phi. Okay, so this is the definition of torque. So let's see if we can actually use that here. So suppose I've got this. Suppose this represents my bicycle wheel, right? And I'll put some spokes on the bicycle wheel just so that we have all kinds of places to apply torque, apply force rather. So this is spokes. And suppose I come along and at, say, this particular location, right here, I apply this with my fingers, some force that basically goes off, say, in this direction. So that's a force, right? And I can ask the question, what is the torque that results from that force? And the answer is that this equation tells you what the torque is. So you have to actually work through what each of these terms are for each time you calculate the torque. So what have we got? Well, we've got the radius, R. So here's the key for torque. This is the fundamental rule for torque and calculating torque. And that is the radius always goes from the pivot point. So I'm going to call this the pivot point, which is just a point in space corresponding to where the three-dimensional axle goes through the board. So the radius R is always measured from the pivot point to the location where the force is applied. That's R in this case. Okay? So I'll say that again. I'll actually write it down because it's so important. R is measured from the pivot point to the location where the force is applied. It's worth taking a whole minute to write that out, because if you remember this rule, you can calculate the torque. And if you don't have this rule in your head, then you will miscalculate the torque over and over again. The key issue is that R is not, I'm not talking about the radius of the circle. I mean, maybe that's big R here or whatever. I'm talking about the radius at which the force that you're interested in is applied. So this is the torque associated with a particular force. So it's R, which in this case would be this distance here, times F, which is the magnitude of this force, so that's great. And then times sine of phi, where phi is the angle between these lines R and F. So in this case, phi, I'll use a, look, I have orange chalk here, so I use my orange chalk here. So phi is, well, it turns out it doesn't matter. It can be either one main angle or the other, but phi basically corresponds to this angle, the angle between R and F, okay? So in this case, I've got some arbitrary angle phi, and I get the torque R and F. So I can calculate this. So sometimes you're given R and F and sine and phi. Other times you just sort of set up the situation and you can ask, right? So for example, if I apply a force at the outer edge of the wheel in this direction, and I've set it up, well, not quite. I set it up so that's perpendicular, then that's the maximum torque. In that case, it's F times radius R times the sine of the angle phi, which is 1. So for this case, the torque is just equal to R times F, because I'm applying here the maximum. In contrast, say I come in and I apply a force right here, and I apply it this way, that force there. Well, the torque due to that force, well, R is that distance here, and F is that, but the sine of the angle between that vector and that vector is sine of 0, so there's no torque here. Zero torque for this one. So most of the time in the problem that you set up, I either give you the angle or you inspect and you see that the angle is either 90 degrees or 0 degrees, whatever it is. And so this part, calculating the angle is usually pretty straightforward. The force, well, usually that's given. Or if it's not given, it's an unknown in the equation that you'll get to later. And usually the tricky part is making sure you understand what R is. And again, R is the distance measured from the pivot point to the location where the force is applied. Notice in particular, R is not a radius. I can apply, in this case, I'm applying a torque to a thing that has a circular shape, so it has a radius. But in general, R is just wherever the force is applied on any given body. And if the body is not round, there's no radius, still R is calculated exactly the same way. Anybody have any questions about that?
One question.
Sure.
Is it significant that the torque is the cross product between R and F?
Well, right. So you're skipping. What you're doing is you're skipping to the what I call the vector definition. So this definition is what I call the scalar definition, which is to say, how do I calculate the magnitude of the torque? And the answer is that I calculate the magnitude of torque according to this equation. And if you're familiar with cross products and dot products, when I take vector dot products, I get cosines, and when I take cross products, I get sines, and that's where the sign comes in. Okay, but what you're asking is if you look and you say, well, okay, if you've taken a class before, and we'll talk about this next week. This is also the definition of torque. That's an equivalent definition of torque. Tau is equal to R cross half, and this is consistent with this. This is the definition, but this is a vector equation, which is to say that torque actually points somewhere. And the cross product basically tells you where it points. And it turns out, as we'll show next week, it points either into or out of the board, and you have to use the right-hand rule to do it. But for now, I don't care which way it points. I just want to know its magnitude. Is that helpful?
Yes, thank you.
All right. So here's the important thing. I've got this. So we'll get to the cross product later. For now, no right-hand rules, no nothing. This is just the definition for just like when we did free body diagrams, we said, let's not worry about the vectors yet. Let's worry about the magnitudes first. That's kind of where we're going. So that's a definition of torque. But just because I have a definition of torque doesn't mean I know what to do with it. The question then is, what do I do with the torque? And the answer to the question is that I can use this equation, this definition of torque, to actually do dynamics. So what do I mean by dynamics? So I'm going to start with Newtonian dynamics. What do I mean by this? There's a bunch of words. That's this far. In the space which I will call translational, which is translational, which is to say with x and y's, this corresponds to everything that we've already done. So translational Newtonian dynamics, the key equation is F net equals m times a. Now, in general, I put a vector on this, but this applies in any one coordinate. So this is basically the one-dimensional version of Newton's law. And we know what Newton's law means now, right? What does this mean? It means that for any body or system with a mass m, if I apply one or more forces, then the body accelerates as a result of the sum of all those forces applied in proportion to the mass. That's what this means. And we have a recipe. We basically figure out what all the forces are, we figure out what the accelerations are, and we solve for the unknowns. So that's what we've done so far. Now, by analogy, I want to do the same thing for rotations. Rotational dynamics. So I need an analogous equation to this equation. An analogous equation, which is to say not the same equation, but an equation that has parameters that are in analogy to this arrangement. So there's an equal sign here. So what equals what is the question. So I'm going to argue that, okay, well, A, we already argued that A is analogous to alpha. So I'm going to put an alpha over on this side. M, well, we need an analogous quantity for mass or for inertia, right? So if I'm taking something and I'm accelerating it translationally, the heavier it is, the more it resists accelerating. In the same way, if something is massive and large, it resists being turned. It's easier to turn a bicycle wheel than it is to turn a battleship, right? So there's some quantity which corresponds to inertia, but it's for rotational instead of translational. And for now, I'm not going to worry about how to calculate it. I'll just give it to you. And I'll call that quantity I for rotational inertia, which is sometimes in your textbooks called the moment of inertia. That's a mathematically precise definition of how it's calculated in some sense of the word. But for now, just think of the letter I as a quantity that is proportional to mass and is somehow related to how big the object is, which we'll get to next week. But it's otherwise something that I will give you. I will hand, if you've got to work a problem, I will give you this quantity. And then what goes on here? Well, if torque is a twist, that's what causes things to turn. It's analogous to a force, which is what causes things to accelerate. So the thing that goes here is the net torque, which is to say the sum of all the torques that are on a body. So let me rewrite it so it's nice and neat here. The net torque, tau sub net, is equal to I alpha. Now here's the thing, this is what students find confusing. You got this equation, and you got this equation. Yes? And what students will often do is they will ask, what's the torque equation? Okay, so there's no such thing as the torque equation. These are two different equations that have different names and different concepts. This thing is the definition of torque. It basically tells you what torque is, right? It's got 3 lines in it. So in other words, it lets you calculate, and notice in particular, it's the definition, it's the definition of the torque associated with a particular force. So, but you remember when we defined work, we said work was equal to defined as a path integral. It's basically a method for calculating this, defining this quantity torque, which depends on force and this vector r, where the force is applied. And you have to, implicit in this is that you have to define a pivot point. Now, by the way, for most objects that we will deal with, the pivot point is obvious. It sits right there in the middle because that's where we're spinning. But you'll see when we get into it next week, you actually are free to choose any pivot point you want. It's just some choices are better. And in this case, the best choice is right in the middle of the wheel, since that's where it's spinning, it's pivoting. This equation is not the torque equation. This equation is not the definition of torque. What is this definition? What is this equation? This equation is literally Newton's second law for rotations. So I will call it N2L rot. This equation is not the torque equation. I'll say it again. This equation is Newton's second law. So how do we use this in general? We use this in general. We say, okay, in order for me to use this, I have to figure out all the torques that are on a body and add them up together. Well, how do I figure out those torques? Each individual torque is defined this way. And then I basically put it in there, right? So in other words, if I were going to apply this, so now I'm going to erase this and kind of apply it. So for example, in this case here, I've got a number of forces on that bicycle wheel. So I'll label those forces. Let's label them nice and neat here. So this force is F sub 1. Well, this force up here is F sub 2. This force here is F sub 3. So we got 3 different forces and on that bicycle wheel that are being applied to cause the bicycle wheel to turn, or at least could in principle cause it to turn. So when I write down Newton's second law for rotations, what I write down is tau net equals I alpha, where I will be given, yay, for now, no need to calculate I. I'll give it to you. And for example, perhaps in this case, I want to know what alpha is. So I have to figure out the net torque. Well, that means I need to find the torque associated with the first force, F1, plus the torque associated with the second force, F2, plus the torque associated with the third force, F3. That's equal to I alpha. So you see what I did? I just broke the net torque into the individual torques. And then once I've done that, then I can use this definition to actually calculate what those individual torques are. So for example, this torque here would be the radius associated with the first one. So I'll call that radius of the first one. In general, I'll call it R1. We'll call this R2. We'll call this R3 the same way. So it's just R1 times F1 times sine of phi1 plus R2 times F2 times sine of phi2 plus R3 times F3 times sine of phi3, and that's equal to I alpha. And if I knew all of these terms, I could calculate alpha. This is the idea. In other words, this equation is the governing dynamical equation. This is the dynamical rule. It is Newton's second law, just in a slightly different form. This is Newton's second law for motion in a straight line, linear, translational. This is for motion of spinning around, rotational, angular. But they're completely functionally equivalent. And you use essentially the same recipe. Okay? So the only thing that we haven't done is we haven't really spelled out what this recipe is in general. So I'm going to not get into too much detail about that because I will spend some time next week and we're a little bit ahead of schedule. But let me just show you one example, which is for the bicycle wheel. The question is really, how do I calculate these things? Well, let me take an example. Let's not do that. Let's save that for next week. I think we're in good shape. Just thinking out loud here. This is pretty much everything I wanted to do. Let me just make sure I haven't forgotten anything. Yeah, I think we actually have time for one more thing. No, I'll save it for, I think I'll save the cross product for next week. We're in good shape. Okay. I think I'm going to call that a day, unless anybody has any other questions. Now we're done a little early, but
R1 and F1
this is as far as we needed to get. And I've posted videos on and review sheet on rotational motion that you want to take a look at before Monday. You've got the homework that's due on Monday. I will have office hours. I won't have them Friday, but I will have them tonight, Saturday, and Sunday. Tentatively all planned at 5:30. I'll post the schedule. Does anybody have any other questions for today?
Can you show R1 and F1 again on the wheel?
Say again?
R1 and F1 again on the wheel. Like,
Yeah, let me do this. I'll draw them nice
up.
and big. Okay. So let me redraw the whole thing nice and big so we can actually figure out what it is. So here's the wheel. And we had 3 forces. So that's my pivot point. And this force here, I labeled F1. And this force here, whoops, not that way. I wanted to go this way. I labeled that F2. And this force over here, which I've had pointed off in that kind of direction, I labeled that F3. Yes, that's my That's the center of my wheel. So let's actually work out the radiuses. So I'll do the radiuses in green. So I've done the forces in white. So this radius here, that's r sub 1, or r sub 3, rather. This radius here, that's r sub 1. And this radius here, that's r sub 2. And then what about the angles? So this angle here, do that in, I guess, orange. That's, move it this way. That's a little better. That's phi3. This angle here, that's phi2. And this angle, well, there's no angle here. That's phi1. Phi1 equals 0 because those two angles are together. Is that helpful? So in other words, for each, so let's kind of work through what this is one at a time. So for example, here, well, if I look at this, I'll notice that R1 here, if I've given you the radius of the circle R, R1 here is equal to R. And phi1 is equal to, well, it's equal to 0 or 180 degrees, right? Yeah, basically pi radians. So that means that the torque due to force 1, which is R times F times sine phi, that's going to be 0. Likewise, for force 2, we've got R2, that's also equal to R, and phi here is equal to 90 degrees. So this term here just becomes R times F2, which I haven't spelled out, times the sine of phi of 2, which is just 90 degrees, which is just 1. So that's great. And then this third term, I've got R3, which is different from R. So I'm going to have to write down R3. Hopefully that's a given. And F3. And then the sine of the angle phi3. All of that is equal to I alpha. And then I can go ahead and start doing my calculation. Is that helpful?
Yes, thank you.
All right. There's one little gotcha here, and I'm deliberately saving this for next week. But when I set up the free body diagrams, but notice in particular this force here. There's 90 degrees. What would have happened if the force was going this way instead of that way? Say the force, say F2 pointed this way. Well, you'd also say 90 degrees. But there's an issue is that this torque is causing the wheel to turn in the counterclockwise direction, right? Whereas the torque, if I applied the force the other way, it would be in the clockwise direction. So not only do you have to keep track of the angle, you have to keep track of the direction. So in this case, all of these torques are causing the wheel to go in, as I've written them, F2 and F3 are all causing the wheel to turn in the counterclockwise direction. So they're all positive. But if I had a force that was going the other way, instead of adding it, I'd have to subtract it. So it's the same kind of thing we do with the free body diagram. We have to keep track of which forces are defined as a positive and which forces are defined as negative, which torques and forces. Okay, I think that's all I got for today. Any other questions about anything for today? We'll go back to my regular chalkboard setup and so forth next week. Okay, and I'll post some office hours. And if you have questions, want to talk to me about any of the work, homework, anything you got, don't hesitate, send me an email. I'll be happy to talk to you. Have a good weekend, everybody.